Okay, any questions? Any general questions? All right, go ahead and turn on your chat. Hello, everyone. Yeah, well, today is lesson 8 and most of 9. All right. Okay, so following the tentative schedule, okay, we are following schedule so far. All right, so today we're going to do lesson 8 and most of lesson 9. Okay, and remember that the homework for lessons 1 through 10, let me get a different color here. The homework for lessons 1 through 10, all right, we'll discuss it next Wednesday, all right? So that's kind of an open forum for students. And then I'll go over the answers very quickly the following Wednesday, September 9th, after the Labor Day holiday. And the first homework set from lessons 1 through 10 will be due Thursday, September 10th over here. That's when it's due, midnight, the end of the day. Any general questions before we start? Okay, any general questions? All right, so let's get started then. Go ahead and ask questions in chat. All right, and I'm going to mute everybody. All right. Okay, let's do it. Today's the 26th. Hi, everyone. In lesson 7, we introduced the average or the arithmetic mean. In lesson 8, we're going to extend this idea to estimating a mean from a frequency table, and we're going to talk about weighted means. What if some values count more than others? Okay, so let's begin by estimating a mean from a frequency table. And we're going to go back to our frequency table for the president's ages. Remember, there were 2 presidents who became president in their early 40s. There were 7 presidents who became president in their late 40s, and so forth. And we obtained that from the original raw data set over here with the 45 presidents' ages. But this list of 45 ages was a bit of a mess. So it was easier to picture the data and picture their distribution by writing out the frequency table. But now let's say that we want to estimate the mean age, the average age. And let's say that we don't want to take all 45 of these ages, add them up and divide by 45. Maybe we don't have time for that. We don't have Excel available. Or maybe we've lost the original data set and we're left with this frequency table. So if we just have the frequency table, how can we estimate the mean if we've lost the original data and we just have the frequency table? So just based on the frequency table alone, how can we estimate the average age of a president on becoming president? Okay, so some ideas here. So basically, these various ages are being binned. They're being placed into classes. So for example, if we look over here, we have the data in a more granular form. They're kind of grainy. So we had 7 presidents who were in their early 60s, okay? Now, here's the thing. Given that we had 7 presidents in their early 60s, when we estimate the sum and then the average, how could we treat these 7 ages? Could we, for example, estimate that they were all 60 years old on becoming president, taking the lower class limit? Well, that might not be wise because that might have the effect of biasing our estimates to the low end. On the other hand, if we use 64 as a common age, if we assume that all 7 presidents here were 64 years old when they became president, then we would be biasing the data on the high end. If we take the upper class limit, it's likely that we'll be obtaining overestimates for the sum and then the average. So instead of taking the lower limit, 60, or the upper limit, 64, what might be more reasonable? How about the average of the lower and the upper class limits? The average, like the midpoint. How about 62 years? Let's assume that these 7 ages here were all exactly 62 years, or perhaps more believably, let's assume that the 7 ages averaged to 62 years. That might be more believable, that the 7 ages on average, they average out to 62 years. So once again, what's the idea here? The age class, 60 to 64 years, has as its class limits 60 years and 64 years. The problem is that we'd be in danger of performing underestimates if we take the 60 years, and we're in danger of performing overestimates if we take the 64 years, the lowest and highest values in the class. So instead, we're going to use the class mark for this class, which is the average of the class limits, the midpoint of the class. So for the age class, 60 to 64 years, the class mark would be the average. Again, how do you take the average of 2 numbers, these class limits? You add them up and divide by 2. We get 62 years. For simplicity, we're going to assume that all 7 presidents' ages in this class were all 62 years old. All 62 years old. Now again, if this assumption seems too strange to you, we'll get the same results for the estimated sum and average if we assume that the 7 presidents' ages averaged 62 years. Again, that's likely to be more believable to you. And the benefit of using 62 years as opposed to 60 or 64 years is that this scheme will not automatically bias our estimated mean towards either the low end or the high end. We're aiming for an unbiased estimate. Okay, so now let's take a look at these classes and now their class marks. So for the age class 35 to 39 years, we're going to use 37 years as our class mark. Granted, that turns out to be irrelevant because we had 0 ages in this class anyway. For the age class 40 to 44 years, we use 42 years, the class mark. That's the average between 40 and 44. There are 2 ages in this class. 45 to 49, we use 47 years, the average of 45 and 49, and so forth. 50 to 54, we use 52. 55 to 59, we use 57. As I just mentioned, 60 to 64, we use 62. 65 to 69, we use 67. And 70 to 74, we use 72. Remember, each of our age classes have equal width. That's why I have 70 to 74 here. Okay, so again, we're going to assume that there were 2 presidents' ages that averaged 42 years. There were 7 presidents' ages that averaged 47 years, and so forth. Okay, now using these class marks and these frequencies, we're going to estimate the sum of the 45 ages and then find an estimate for the average of the 45 ages. By the way, remember that these frequencies have to add up to the population size, capital N or 45. The frequencies are values for F. The summation of the frequencies better be capital N, the population size. These better add up to 45. We're making sure that our table is accurate. It's a check. Okay, so how do we go about estimating the sum of the 45 ages using these class marks and these corresponding frequencies? Okay, well, there were no ages in this lowest class. There were 2 ages in this next class. Again, we're assuming that these 2 ages were 42 years, or they averaged to 42 years. And then these 7 ages, we're assuming, these 7 ages here, we're assuming averaged to 47 years, or more simply, they were 47 years. We're assuming these 7 ages were 47 years. Whether you think of the 7 ages as being exactly 47 years or just averaging to 47 years, we're going to end up with the same result, and so forth. So if we do that, here's what we get. A long way to estimate the sum would be to add copies of the various class marks. So again, we're assuming that there were 2 copies of 42 years. So what would be the contribution to the estimated sum? It would be 42 plus 42 in blue here. There were 7 ages in this class. We're assuming that all 7 ages were 47 years old, or they averaged to 47 years old. Either way, we would take the sum within this class to be the following. We would take the 7 copies of 47 here and add them up. And that would be the contribution to the sum of the 45 ages. Okay, and then there were 13 ages we're assuming were 52 years or average to 52 years. So we take 13 copies of 52, add those up, and so forth. So then, by the time we're done with this, right, we end up with this huge sum here, this huge sum, which turns out to be 2,480 years. Bear in mind, there's only 1 age in the highest class, and the class mark was 72. We only had 1 copy of the 72. Now, again, when you add all these up, our estimated sum would be 2,480 years. Just for kicks, if we were to go back to the original data values, these here, what would be the sum? Let's ask Excel. I have the actual ages here, the raw data. Let's ask Excel. The actual sum, B2 to B46. Again, we're rounding down ages to the year, right? Look, our estimate for this, okay, so the actual sum based on our Excel spreadsheet was 2,475 years. And our estimate was 2,480 years. That's pretty close. Now, hold on. You might be asking, but this is so much adding. I may as well just go back to the original data set and add these all up. How can we make this much more efficient? How can we make this much more efficient? For example, the 7 copies of 47. The 7 copies of 47. What's a fast way of computing this sum here? Taking the 47 copies of 47 and adding them up.
7 copies.
Instead of adding them up directly, what could we do? We could just take 47 times 7, or vice versa, 7 times 47. And we can do that for each of these classes. So for example, in this second class here, we can estimate the sum of the ages by 2 times 42. 42 plus 42. For this third class here, we can estimate the sum of the ages in this third class by taking 7 times 47. And so forth. So here would be a much faster way of doing it. We're using the fact that repeated addition can be represented with multiplication. Here's a much faster way to get the estimated sum. For each class, multiply each class mark, the X value, by the class frequency, the F value, to get the class sum, F times X. These are values of F times X, 2 times 42, 7 times 47, and so forth. And these class sums would be the sums of the ages in the class. So this here would be the estimate for the sum of ages in this third class. Right. So then we would get this. The computation arises from a zigzag. And we see these zigzags a lot in our statistics class. So how do we get our estimated sum? We do 0 times 37, well, that's 0 anyway, okay, plus 2 times 42, that's 84. That's our estimate for the sum of the ages in the second class, 2 times 42, plus 7 times 47, plus 13 times 52, plus this times this, plus this times this, plus this times this, plus this times this. And then you'll get our estimated sum. So by doing this zigzag, we obtain an estimated sum, again, of 2,480 years. The exact same result as if we had done it this way. So the zigzag method that you see over here is just a much faster and more efficient way of performing this grand addition over here, where we're treating repeated additions as multiplication problems. So here we have 7 times 47 instead of adding all this stuff up. All right. Now, again, folks, how do we take an average? we take our sum or estimated sum and divide by the population size, capital N, the sum of the frequencies, 45 here. There are 45 ages. So we now divide the estimated sum by the number of ages, the population size, to get our estimated mean. Here's our formula. The estimated mean is given by the estimated sum divided by N. The population size, the number of values, 45. 45 was the population size, capital N. So using professional notation, don't get a nosebleed here. On the top, how do we get our estimate for the sum? It was from that zigzag. And we often denote zigzags by summation something times something, right? Summation f times x plus f times x plus f times x plus f times x, and so forth. Technically, we'd have subscripts. It would be f sub 1 times x sub 1 plus f sub 2 times x sub 2, and so forth. But we're not going to get that detailed. We're adding products. It's this times this plus this times this plus this times this, and so forth. Summation f times x, that's the zigzag. And you can go either way. You can also go the other way. You can go 37 times 0 plus 42 times 2. It doesn't matter. Okay? And in fact, you could reverse the order. Both multiplication and addition are commutative. There are various orders you can perform these in. For example, you could switch these guys, or you could reverse the order. That's fine too, of the sum. All right, anyway, our estimated sum was 2,480, right, from the zigzag. So from the zigzag in green, that was 2,480 over here. That was that zigzag guy up here, over 45. And we get to the nearest tenth of a year. Remember, we go one decimal place further. We get about 55.1 years, our unit. So our estimated mean for the present ages was about 55.1 years. In fact, if you go to our Excel spreadsheet, what was the average, the mean? The actual mean was equals average, B2 to B46, hey, 55.0. For all practical purposes, we got it. Because remember, when we enter these various ages, these were already rounded down, right? There's already a lot of rounding going on here, right? I mean, someone who was 47 years and 11 months, we round down to 47. There was already a bunch of rounding going here by months, right? So, I mean, 51.1 years versus 55.0 years from our Excel spreadsheet. For all we know, maybe 55.1 years was more accurate if you throw in months and days. In any case, I think we did a great job. Okay, this really matches up with our Excel spreadsheet, right? Excel says 55, we got 55.1. Come on, with months and days, we might have been more accurate this way. All right, estimating means from a frequency table. Next up, weighted means, including your GPA. Next time.
All right, any questions about this before we go on to GPA, which is very interesting? Any questions? Any questions? All right, let's go on to your GPA.
Hi, everyone. Let's now talk about weighted means. In some data sets, some values are more important than others, and we use weights to measure the relative importance of data values. So think about it. In a class, if you get an A on a midterm that's worth 10% of the class grade, and if you fail a final that's worth 90% of the class grade, does that mean that things balance out and you pass the class with a C? Not necessarily, because the final is worth a lot more than the midterm. I'd say you probably failed. All right. Now, as a student, you could argue that the most important number, the most important weighted mean in your life is your overall GPA. All right. For now, let's just look at the GPA for one term. Let's say you receive the following grade report for a term. What then would be your grade point average, your GPA for the term? Let's say that you took a math class, a chemistry class, and a biology class. Not that it matters statistically. That won't affect the computations here, but I just want things to refer to. Now, what will be important will be the weights here, which will be the numbers of units for these classes, and the grades that you got in these classes. So the key thing here is not so much that you took a math class, it's that that class was worth 5 units. That was the weight for that class. Your chemistry was weighted 4 units. Your biology class was weighted 3 units. And here you have the corresponding grades. It's not so much that you took a math class, it's that you took a 5-unit class. In a 5-unit class, you got an A-. In this 4-unit class, I don't care what subject it is, in this 4-unit class, you got a D. In any case, you should be ashamed of yourself. In this 3-unit class, you got a C+. I can tell right now you probably shouldn't be pre-med, don't operate on me, but let's figure out your GPA for the term. Now, we would expect that overall, your math grade, the grade for the 5-unit class, will have more of an impact on your GPA, but bear in mind, outliers could also matter. If you had gotten like an F in your biology class, whatever that means, then maybe that could have quite as well.
I'm not sure I understand.
Okay, wait. Yes? Did someone want to talk, or did you want to chat? Any questions? All right.
You'll understand, Siri. Okay.
Oh, wait a minute. It's not.
All right.
Oh my gosh, that was Siri. I was talking to Siri. All right.
So how do we compute the GPA? Based on this table. By the way, the minus here and the plus here are referred to as grade modifiers. At Mesa, it was decided many years ago that students didn't want modifiers like minuses or pluses. I think in part because students were afraid that they would get more A minuses than A pluses. They wanted an A to be an A. Okay, now a problem you might have is, wait a minute, I see an A minus, I see a D, I see a C plus. I don't see numbers. How do we put these into a formula? I don't see numbers here. Right now, these represent what kind of data? Do you remember? We call this ordinal data, and we can recode them numerically. All right, the grades here are ordinal data values. They are non-numeric as they stand, but there is a natural order. So as a student, you would prefer an A plus to an A, you would prefer an A to an A minus, you would prefer an A minus to a B plus, and so forth. Unless you want to tell your parents, I want to quit school and go somewhere. All right, I'm assuming you want a better grade. Now again, we're going to recode these grades numerically as sort of quantitative numeric data, although it's debatable whether or not these are fully quantitative. They will at least be numeric. Now, the standard is that we say that an A is worth 4 grade points, a B is worth 3 grade points, a C is worth 2 grade points, a D is worth 1 grade point. Sometimes D's can matter. An F is worth 0 grade points. And in some settings, a D might even be passing, but normally A's, B's, and C's would be considered passing. All right. Now, if we allow modifiers, often a plus modifier will raise the value of a grade by 0.3, although this isn't standard. Some institutions might use 1/3, but a 0.3 can be written as an exact decimal. The minus modifier typically lowers a grade value by 0.3. So for example, what would an A minus be? If you get an A minus in a class, how many grade points would that be? An A would be 4 grade points. How many grade points would an A minus be? Well, remember we got an A minus in math, or you got an A minus in math, okay? So an A is worth 4 grade points, but since you got an A minus, you subtract 0.3, 4 minus 0.3, that's 3.7. So an A minus would be worth 3.7 grade points. So a student might say, oh, I wish we didn't have modifiers. Then I think I would have gotten a straight A. That would have been 4 grade points. All right. So let's work out the GPA. What would be the corresponding grade recoded as grade points numerically? Although they might not be fully quantitative in the sense that although grade point wise, an A is twice a C. I mean, can you really say that an A is twice a C in principle? Maybe not in principle, but in terms of grade points, yeah, an A is twice a C in terms of grade points. Assuming no weighting or anything like that. All right. Well, your A minus in your math class, that's 3.7 grade points. The D you got in the chemistry class, that was 1 grade point. Now, what about the C plus you got in the biology class? A C plus is how many grade points? Well, a C is normally 2 grade points. A C is normally 2 grade points, but because of the plus modifier, we're going to add a 0.3. So a C plus would be 2.3 grade points. So then this person might appreciate that modifier there. Okay, a C plus will be 2.3 grade points. Your math class was 5 units, your chemistry class was 4 units, your biology class was 3 units, okay? So how many units did you take? The sum of the weights was 12. You took 12 units for the term, the semester, or quarter. All right, now folks, in order to compute your GPA, your grade point average for the term, do you take these 3 values, 3.7, 1.0, 2.3, do you add them up and divide by 3 to get your GPA? The answer is no, because then you'd be ignoring these weights. When would the answer be yes, though? When would that work? To take the sum and divide by 3. When would that work to get your GPA? If what were true with these numbers of units, if what were true of the weights. If these were all equal in weights. So if these were all 5-unit classes, for example, then these grade points would be equally weighted, and yes, you could actually add these 3 numbers up and divide by 3, because the 3 classes are equally weighted. However, here, the 3 classes are not equally weighted. That scheme will not necessarily work, and we would not expect that it would. So what do we do? What do we do? It's very similar to the president's example. Right? So imagine this. Because the math class is worth 5 units, okay, we're going to consider this. Because the math class is worth 5 units, imagine writing 3.7 on 5 slips of paper. Imagine writing 3.7 on 5 slips of paper. All right. Similarly, imagine, because the chemistry class was a 4-unit class where you scored a 1.0, all right, imagine writing a 1.0 corresponding to the D on 4 slips of paper. And then likewise, imagine writing the 2.3 here. Imagine writing the 2.3 here on 3 slips of paper. Okay, so we have a total of 12 slips of paper. We have these 12 slips of paper here, all right? And the number of times that a grade in numeric form is copied, that corresponds to the corresponding weight. The weight gives you the number of times, the number of copies of that corresponding numeric grade. So our weighted mean, or weighted average, will then be what we get when we take the numbers on these 12 slips of paper, add them up, and divide by, not by 3, but by 12. We have 12 numbers on 12 slips of paper. We get the weighted mean, or weighted average, by adding up the 12 numbers and dividing by 12. And that'll be the grand sum. But there's a fast way of doing it. Remember the president's ages. Instead of taking these 5 copies of 3.7 and adding them all up, why not just take 5 times 3.7? Repeated addition can be efficiently done as multiplication. 5 times 3.7. And those are your total grade points from your math class where you got an A- for that 5-unit class. Likewise, 4 times 1, that's a total of 4 grade points in this scheme when we work out the grand sum for your chemistry class. For your biology class, 3 times 2.3 or 6.9, those are your total grade points from your biology class as we calculate the grand sum. So the grand sum here is obtained by doing a zigzag, the zigzag. All right. So here's the idea behind the zigzag. We've seen this before, and we'll see it again. It's this times this, plus this times this, plus this times this. There are various orders you can do it in, but bottom line, it's 5 times 3.7 plus 4 times 1.0 plus 3 times 2.3. It's the zigzag, like what we do with the presidents. And that'll give us the grand sum of the numbers on these 12 slips of paper. So the row sums for each class, all right, that's given by W times X. The weight, the number of units, times your grade as a number, 3.7 for an A-. Okay, so each of these row sums is given by this product, W times X, for class number 1, class number 2, and class number 3. The grand sum is given by summation, W times X. We're adding up all these class sums. Literally, these class sums. All right. So when we do that, when we do the zigzag, this times this, plus this times this, plus this times this, we get a grand sum of 29.4 grade points. That's not an estimate. That's the actual grand sum where you apply this scheme. But now we take this grand sum of 29.4 grade points, and what do we divide by? We don't divide by 3, we divide by 12. We had 12 numbers here on 12 slips of paper. All right, so your GPA, your weighted mean, is obtained by taking the grand sum, all those numbers on all those slips of paper. We divide by the sum of all the weights. That's the total number of units you took for the semester, 12 units, right? So the grand sum is from the zigzag. Summation, W times X. This times this, plus this times this, plus this times this. Summation W is the number of units you took. You took 12 units during the term, during the semester or quarter. So you divide 29.4 by 12 and you get, this is exact, 2.45 grade points. Although, because these were written out to 1 decimal place here, you would round this off to 2 decimal places anyway. 2.45 grade points. Which, by the way, in terms of letters and maybe modifiers, what would that be? Would that be like an A- or what? What would that be? Well, a 2.45, that's a bit higher than a C. We're talking about like a C plus maybe, right? A C plus to a B minus. Is that good enough for medical school in the United States? Maybe not. Maybe not. Maybe in Fredonia, but not in the United States. That's probably not good enough for med school in the United States. It might be good enough to pass and get your diploma if that's all you care about, but probably not good enough for med school. Then again, you probably could have told that just from looking at the grade record here. Maybe it's time to change majors. Don't tell your parents I said that. Okay. Next up, what is the most common question I get from students? And then you'll be able to answer that question for yourself. Maybe Canvas can too. Next.
All right, so while we're at it,
Next time. Hi, everyone. So what is the most common question I get in a class, especially in the last few weeks? What do I need on the final to pass the class with a C maybe, or to get a B, or to make the A? What is needed on that last item to obtain at least a particular weighted mean? What do you need on the final to do whatever? All right, let's say this is your grade report so far in a class. And let's say there's no homework. The entire grade is based on 5 exams. 3 quizzes, each worth 10% of the course grade. A midterm, worth 25% of the course grade. And a pretty big final, that's worth 45% of the course grade. So these are the only 5 components to your course grade. Not in our class, but in this hypothetical class at university. Now let's say that you've taken everything except for the final exam and you have your scores for 4 of the 5 exams. Everything except the final. You received scores of 75 points out of 100. So basically you got a 75% on quiz 1. In order to normalize the scores, I'm going to assume that all these score totals are I'm going to assume that the maximum possible score on each of these exams is 100 points. So you can basically think of percent when you look at these numbers. So you scored 75 out of 100 points, or 75% on quiz 1. I don't care if it's 750 out of 1,000 points. Bottom line is you scored 75% on quiz 1. You scored 80% on quiz 2. You scored 100%, you aced, you got a perfect score on quiz 3. You got 95% on the midterm, which was bigger than each of the quizzes. Now you still have to take the final. Out of wishful thinking, I'll put the letter little a there. That's an unknown. We'll treat it as a variable for now. You have not taken the final yet, so it's unknown at this time. Out of wishful thinking, we'll put a little a there. That's going to be your score on the final, basically indicating your percent. You have not yet taken the final, so we have labeled the final score with a hopeful little a. And the question is, well, how well do you need to do on the final in order to get an A overall in the class? Assuming that an A means getting at least 90% of the total points. That is, getting at least a weighted score of 90 points in the overall class. Question, what must you get on the final to get at least 90% in the course overall? In other words, at least 90 points as a weighted mean or weighted average, if we say that the course overall is out of 100 points as a course total. So let's do this. So how can we represent your grade in the class here as a function of little a? So whatever little a turns out to be, how can we express your grade in the class, your weighted grade in the class, where the final is worth a lot more than the other exams? All right, again, we're asking about a weighted mean. So the final is worth more than the midterm is worth more than each quiz. In fact, it's worth about all 3 quizzes put together. So we're going to write the exam weights as decimals first off. So 10% is 0.10 or just 0.1. 10% is 0.1, 10% is 0.1, 25% is 0.25, 45% is 0.45. Now the course average is going to be represented by this somewhat familiar formula here. This familiar formula. Summation W times X, that's the zigzag, over summation W. Summation W times X. W here is the weight of each exam. So again, it's going to be 0.1 for quiz 1, 0.1 for quiz 2, 0.3 for quiz 3, 0.25 for the midterm, and 0.45 for the final. Writing the weights in decimal form. These add up to what? Well, these will add up to 100%. These will all add up to 1. Right. So the sum of the weights is 100% or 1 down here. Okay, that's the sum of the weights. Before, it was 12 units for our GPA when we were computing GPA. Here, since these are all proportions, right, the total of these will be 1 or 100%. So we're going to write a 1 down there, which means that we don't have to write it at all. If you're dividing by 1, you don't really have to think of this as a fraction. Right. Now, summation W times X, that's the familiar zigzag. It's this times this, plus this times this, plus this times this, plus this times this, plus this times this. It's the familiar zigzag, like what we did for GPA before. Summation W times X, that's the zigzag. And we're going to divide by 1 because that's 100%, the sum of these weights. All right, so we do that. Again, you don't need the divided by 1 over here, all right? From the zigzag, we get, all right, again, 0.1 times 75 plus 0.1 times 80 plus 0.1 times 100 plus 0.25 times 95 plus 0.45 times A. And you can think of this expression that we get, 49.25 plus 0.45A, that expression represents your overall weighted course average out of a maximum possible of 100 points, expressing your course average as a function of little a, which represents
you may not be able to see
your
it, but
unknown score on the final. That's yet to be determined. Now let's talk about this expression some more. Let's talk about the 49.25. What does that mean? That means that so far, you have collected 49.25 weighted course points on your path to, what do you want? You want 90 points or above as your weighted mean or weighted average for the overall class. We're saying that so far, you have 49.25 of your weighted course points. So you're about halfway there. So remember, on your first exam, on quiz 1, you got 75 points, or 75%, on a 10% quiz. So what does that mean? So you got 75 points out of 100 points, basically, on your first exam, but that quiz is only 10% of the total course grade. So because the quiz is only worth 10% of the overall course grade, what you've accumulated here, I'll put this in blue. What you've accumulated here is not 75 weighted points for the overall course, but only 10% of that, 7.5 points. Remember, what's the finish line? You want to get at or beyond 90 points as your weighted course average. If you got 75 points on a 10% quiz, you haven't made 75 weighted course points yet. You haven't gotten that far. You've only made 10% of that, 7.5 weighted course points. So on your trek, your path towards 90 points or more as weighted course points, as a weighted course average, if you make 75 points on a 10% exam, you have accumulated 7.5 weighted course points to your overall weighted course average. From here, if you make 80 points or 80% on a 10% quiz, then you've accumulated 8 additional points on your trek to 90 points or above. So far, you've made 15.5 points in terms of your weighted course average. So after the first 2 quizzes, you've accumulated 15.5 weighted course points on your trek to 90 points or above. On quiz 3, you aced that thing. You got 100 points on that third quiz, but it's only a 10% quiz, so it only counts 10 additional points. But you appreciate them, okay? Because now, instead of 15.5, you're now at 25.5 weighted course points on your trek to 90 or above. Over here, you got 95 points on a 25% midterm. So these points will count more. What is 25% of 95? Well, I'll ask a calculator. 0.95 times, it's 95 times 0.25. That's going to be 23.75. So you accomplish a lot here. When you got 95 points on that 25% midterm, you've accumulated 23.75 more weighted points on your trek to 90 points or above as your weighted course average. Add those on to the 25.5, and right now you're at what? You're at you're at 49.25. Exactly. So by the time you're done with the 3 quizzes and the midterm, you have accumulated 49.25 weighted course points on your trek towards 90 points or above as your weighted course average. Now, what if you don't take the final at all? Some people might ask, so what happens if I don't take the final at all? Well, you plug in 0 for A. That means you zap this term over here, which means that your overall course average will be 49.25%, or 49.25 out of a maximum possible 100 points for the course. That's probably enough. So you probably want to take the final, unless your goal is to drop out of college. All right. But anyway, this is a handy dandy expression, because then you can ask questions like, what happens if I get, what happens if I score 10 points on the final? Well, that will add 4.5 weighted course points. That'll take you to like 53.75. That won't be enough. Now, if you ace the final, if you get 100 points on the final, well, then that adds 45 more weighted course points to your total. That'll definitely take you to an A. All right, that's going to take you to what? 94.25? Well, that'll absolutely do it for you. So you can plug in various numbers, okay? Ask yourself, okay, if I get such and such on the final, what will be my overall weighted course average? So if we don't take the final, we're pretty much failing, right? If we ace it, we'll get an A. The question is, what is the minimum score we can get away with in order to get an A overall for the class, assuming a straight scale? So we want this to be 90 points or above. By the way, as a matter of algebra, do not combine these two numbers. A lot of students try to combine these two numbers right off the bat. Don't do that. Because remember, by the order of operations, oops, the 0.45 and the A are closely tied together by multiplication. Multiplication precedes addition. So do not add these two. The 0.45 is very much married to the A. All right. But that's good so far. All right, we have here an expression. This is the course average. This is your course average as an expression represented as a function of A, your score on the final, which we don't know yet. All right. So now, what is the minimum score that you need in order to get an A in the class? Really, we're solving an inequality. We need this course average to be at least what? At least 90. A weighted course average of 90 points out of 100 points possible, kind of like 90%. I don't want to say 90% though, because people might think 0.9. You don't put 0.9 there. You want your weighted course average to be at least 90 points. So that's the inequality that we solve. Now, one note, some of you might be going, oh, I hate these decimal points. Do I have to put 0.1, 0.1, 0.1? Can't I just put like 10, 10, 10, 25, 45, 10, 10, 10, 25, 45. Well, you can do that. But if you do that, then what's the sum of the weights? It won't be 1, it'll be 100. But that is legal though. Okay, that's another way of getting the same expression down here for your course average. So you could go just straight up without the percent symbols or converting to decimal. You could just say straight up, it's going to be 10 times 75 plus 10 times 80, plus 10 times 100, plus 25 times 95, plus 45 times A. But you have to divide that big old sum by 100, the sum of these weights. But that's okay, you could do that. And if you divide each of these terms on top by 100, you're back to the original. 4,925 divided by 100 is 49.25, plus, and then 45A divided by 100 is 0.45A. So you end up with the same expression as before. All right, I don't care how you get here, just show your work. You can do it either way. All right, again, we're going to solve this inequality. I need this, you need this, to be at least 90 points overall as your weighted course average. What is the minimum value of A that will allow you to do that? Although I always tell students, look, study as best you can. You can't predict. You can't say, okay, I've studied 3 hours and 25 minutes. That means I know I'm going to get a 93 on the exam. You can't say that. Do the best you can. Come on, folks. You can't predict based on how much you've studied so far. All right, anyway. So here's how we'll phrase the question. What are the values for A on the final that will yield a weighted score average of 90 points or above for the course? Okay, we're going to solve an inequality. We want to know what values for A will lead to a course average, that's the course average in terms of A. We need that to be at least 90 points. Now we don't like these decimal points over here. So it looks like we're going to clear the decimals if we can multiply both sides by 100. Remember, this is 0.45 times A. These numbers are both written to 2 decimal places. We can clear the decimal points by multiplying both sides by 100. If you have this in the fraction form over here, that's more clear. If you put that fraction on the left, then it becomes more clear. Multiply both sides by 100. All right. So then, this times 100 is 4,925. This times 100 is 45A. Or you just get the numerator up on top here, 4,925 plus 45A, right? And we need that to be at least, don't forget to multiply the right side by 100, we get 9,000. 90 times 100 is 9,000. So now we're solving this nice linear inequality here. All right, this was also linear inequality, but this is much nicer. And then what do? We ultimately want to solve for A. So we want to isolate this term, 45A. How do we get rid of the number here on the left? Right now it's being added to this term I've circled. So to undo that, let's subtract it. We're going to subtract 4,925 from both sides. All right, when we do that, we basically cancel out over here. We're left with 45A on the left. Has to be greater than or equal to 9,000 minus 4,925 is 4,075. Now, how do you get A all alone on the left side? We want to divide both sides by 45. Divide both sides by 45. I'm showing this for your benefit. You can go straight from here to here. 45A divided by 45, you're left with A on the left. Technically, you should put little ones here. You should indicate what's left, all right? We're left with 1A. 1A on the left has to be greater than or equal to, and then 4,075 divided by 45 to, say, 1 decimal place is 90.6 points. So little a has to be at least 90.6 points in order for you to get a weighted course average of 90 points or above. You need to score at least 90.6 points on the final to get at least 90% of the maximum possible performance in the course overall. But now, wait a minute. Very few instructors grade to the 0.1, 0.2, 0.3. We mostly grade in non-negative integers. Hopefully you won't get a negative score on your test. But to be very safe, what score would you need realistically on the final? If it's out of 100 points, what score would you need realistically on the final to get an A or above, guaranteed? To be super safe, you should round this up. Even if this were 90.001 points, to be super safe, you might want to round this up in this setting. To be super safe, you want 91 points or above. So if the teacher only grades in integers, and most of us do, then as a practical matter, we could say that you need at least 91 points to be guaranteed an A. But because if you score only 90 points, then this course average here will be just a little bit below 90. It might be 89 point blah, blah, blah. But bear in mind, your teacher does not necessarily have to round up scores, okay? So if you get exactly 90 points, then if you get exactly 90 points on the final, then this here, your course average, will fall a little bit below 90 points. It'll be 89 point something, but you're not guaranteed to get an A. If your teacher doesn't like you, or you talk too much in class, then you might end up with a B. So to be super safe, round up 91 points to be guaranteed an A. All right, so far we've talked about measures of center, including means, Next, we're going to talk about measures of variation or spread. Next time.
All right. Any questions about that? So then you won't have to ask me this question near the end, right? I tell my stat students, hey, you should know how to do this, right? By the end of the class, what do you need to score on the last thing in order to get such and such in the class? Okay, so that helps me out. Any questions before we go on to measures of variation? Measures of variation. All right, let's proceed.
Hi, everyone. In lesson 9, we're going to talk about measures of variation or spread. How spread out is the data? Before we talked about measures of center or a representative measure for data, quantitative data, now we're going to talk about measures of spread. In fact, there are 4 measures of spread that we'll discuss. One of them is fairly straightforward. Let's say that we have a list of 100 test scores. How would you measure the spread of these scores if you had maybe 15 seconds without a calculator? Well, you might try to find the highest score, the max score. Someone did ace the test, assuming this was out of 100 points. I hope it's out of 100 points, not 1,000 points. And then look for the lowest score, the min score, the 13 over here, 13 points, and then take their difference. 100 minus 13 is 87 points. That's called the range, perhaps the simplest measure. But think about some potential drawbacks to that measure. All right, now let's make things easier. Let's go from 100 test scores to 5. Okay, so let's go all the way down here. So the 5 students in a class take a test. Their scores in points are as follows. This is the same data set as before. 80 points, 76 points, 100 points, 83 points, and another 100 points. How can we find a single number that tells us how spread out the scores are? A measure of spread or variation. Now we're going to look at 4 possibilities for measuring the spread or variation of a quantitative data set, such as this. Now, one thing to keep in mind is that all 4 measures are going to be non-negative in value. So if I ask you to calculate one of these measures, if you get a negative number, you know you messed up. All these measures of spread or variation will be non-negative. And the only way it could be 0 is when what happens? When is the only situation when the measure of spread or variation would be 0? If all 5 test scores are the same. For example, if all 5 students score an 80. Hopefully it wasn't because of cheating, but if all 5 test scores are the same, then our measure for spread or variation will be 0. Otherwise, these measures will all be positive. All right. Again, the most straightforward measure for spread or variation is the range, which is calculated by taking max minus min. The highest value you see in the data set minus the lowest value you see in the data set. So in example 1, all right, we see that the maximum, the highest score in the data set is 100 points. There's a tie, in fact. And the lowest score that we see is 76 points. That's going to be the min score. Maybe not the minimum possible, that's 0 points, but this is the minimum score we see in the data set. That's what we mean by the min. And remember, don't just take the leftmost value because you feel like it. You would only do that if the data values were sorted from lowest to highest. Here, this data set is not sorted. All right, so 100 minus 76 is 24 points. That's the range for this data set. 24 points. That's what separates the highest score from the lowest score that we see. So a pro to this is that it's very straightforward. It's very quick and easy, assuming that you can find these scores, or at least have Excel figure these out for you. I showed you the max and min functions. And in fact, I can show you it on an Excel spreadsheet, all right? So, okay, let's remember, how do you find the max score, all right? Well, it equals max parentheses A2 colon A6, 100 points. How do you find the min? Equals min A2 colon A6, right? So those would be the commands. Command here would be max A2 colon A6. Command here would be equals min A2 colon A6. And the range would be the difference. A12 minus A13. Or do in one fell swoop equals max A2 colon A6 minus min A2 colon A6. All right, 24 points. All right, so the pro is that the range is quick and easy to find, assuming that you or Excel can find the max and min pretty quickly. I realize that without a computer, by staring at this, it might take you a while to find the min at least. The max you can find pretty quickly. It might take a while to figure out the 13 points is the min, right? So pro, quick and easy to find, and also it seems like a natural measure. But what is a key con? The range is extremely sensitive to what? It's extremely sensitive to outliers. So for example, if you have a physics class with the ghost of Albert Einstein and Bart Simpson, then the range might always be 100 points. Okay, so what are some other measures of spread? The variance, which we'll abbreviate VAR. The standard deviation, which is always the square root of the variance. And this is the most commonly used measure of spread. We find it most often in formulas. But it takes a while to compute by hand. And also the interquartile range, the IQR, which we'll discuss later on in a later lesson. Okay, so next up, we're going to talk about notations for variance and standard deviation. And it depends if you're dealing with a population data set or a sample data set. Next time.
Okay, any questions before we go on to the notation and calculations? Any questions? Any questions? All right. Oh, before I forget, I'm going to show you something kind of cute here. All right. So let's talk about some notation, which is a bit drier, I admit.
Hi, everyone. So what notation do we use? Well, remember, we use capital N to indicate the population size for a population data set. We use little n for the sample size for a sample data set. So population size is capital N. Sample size is little n. Now remember, for the mean, a measure of center, the population mean is given by the Greek letter mu. Remember that we typically use Greek letters to denote population parameters. The Greek letter mu represents population mean. The Greek letter lowercase sigma, this here is lowercase sigma. It's the little brother of this uppercase sigma over here, which indicated summation. Lowercase sigma denotes population standard deviation, or SD. It's like a sideways 6. And remember, the standard deviation is always the square root of the variance. I'll even type it out. The standard deviation is always the square root of the variance, whatever the context, right? Which means that the variance is always going to be the square of the standard deviation. The population variance is given by sigma squared. All right. Now, in blue, I'm going to denote the sample statistics, which are normally denoted with Roman or English letters, which you're used to. So sample size is little n. The sample mean is x bar. The sample standard deviation, or SD, is S. The sample variance is therefore S squared. These are lowercase s's. Now, ultimately, we care about the values for a population mean, a population standard deviation, and or a population variance. We really care about these population parameters on top and their values. The sample statistics on the bottom, they're a means to an end. So if we have a huge population where we cannot do a census efficiently, if we have 100 million registered voters in Fredonia, we might want to take a sample, a poll of, say, 1,000 voters, in which case little m would be 1,000. And in that poll, well, we might be rude and ask, what's your age? What's your age? So we could find the sample mean, right? The sample standard deviation and the sample variance. But remember, the goal of calculating these sample statistics is to approximate the values of the population parameters. We only care about the sample mean insofar as that it helps us estimate the population mean. We don't care about the sample mean in and of itself. We only care about it insofar as it helps us estimate the population mean. That's the purpose of the sample mean. The purpose of X bar is to estimate mu. Likewise, the purpose of the sample standard deviation, S, is to estimate the population standard deviation, sigma. That's where the inference comes in. And also, the purpose of the sample variance, S squared, is to estimate the population variance, sigma squared. So in inferential statistics, we're going to use these sample statistics, X bar, S, and S squared, to estimate the values of these population parameters, mu, sigma, and sigma squared. Next up, how do you calculate population, standard deviation, and variance? And how do you calculate sample, standard deviation, and variance? Later on.
Okay, any questions about these notations before you go on? Because you have to make sure that you familiarize yourself with these notations, okay? So you shouldn't ask me down the line, you know, what's that you with that needs a haircut? I'll answer it for you because we're not testing, right? But yeah, you should be aware of these notations. Any questions before we go on? We are going to do some calculations. Although we won't be doing too many of these, like standard deviation calculations, too much throughout the semester, still, I want you to get a flavor of it. Okay, let's go on.
Hi, everyone. So for population data, how could we calculate a population variance or population standard deviation?
One moment, I'm losing the captions. Let me try to.
We're going to go through this.
Let me see if I can get the captions here. Sometimes the captions fail us. Otherwise, the Zoom video might actually pick it up. Okay, let me see if I can get this. Oh, there we go. Okay, let me see if.
How could we calculate a population variance or population standard deviation, or SD? And we're going to go through this, even though we're not going to repeat these calculations all throughout the semester. That'll be quite tedious. But we should go over the ideas behind how to compute these and go through the process. Now, as we compute these, we're also going to need to find the population mean at some point, mu. And since we have population data, census data at hand, we won't have to deal with samples. We don't need this stuff. All right, at least not for now. So what's the idea behind population variance and standard deviation? All right, now the idea is we're going to focus on the population mean mu as a reference point. So we have a flag planted at the mean mu, right? And we want to measure the spread of the data values around the mean. So assuming that we have the same scale on these two axes, the mean here, planted at the same number, what data set would exhibit higher variation or spread? Well, probably the data set down here. They're more spread out about the mean. Like over here. Now it's true that they have the same range. The two data sets here have the same range. Max minus min is the same. And yet we have the sense that this data set here is going to be more spread out than this data set. They're more spread out about the mean. Well, let's see why. It does turn out that the second data set would have a higher variance or standard deviation. All right. So here are the steps. It's a recipe. Given capital N data values, x of 1 through x of n, step 1 is to find the population mean, mu. So I'm going to write out the steps in the left column. The notation will be in the right column. This is our classic formula for population mean. You take the sum of the data values, divide by the population size. And then you find the deviations from the mean by subtracting the mean from all the data values. All right. So we're going to recenter the data so that instead of mu, the new data set will be centered at 0. That's a way of standardizing things. We're going to subtract off the population mean from all the data values. All right. We're going to square these deviations. Below a column for these values. The variance will be the average of these square deviations. We take the sum of these values from step 3. We take these values, take the sum, add them up, divide by n. The standard deviation is always the square root of the variance. So ultimately, it comes down to this formula for population standard deviation. Obviously, an example will help. Let's look at an example. All right, let's go back to the 5 test scores from before. I have them in this column, and they don't have to be sorted. So let's say we have the 5 test scores for all 5 students in the class. This is census data. We have all the population data we want. The first step is to work out the population mean, mu. We get that from adding these up and then dividing by 5. We get exactly 87.8 points. In any case, we want to round off to 1 decimal place anyway. So that's step 1, finding the population mean. And then what do? We find the deviations of these scores from the mean by subtracting off the mean. So 80 minus 87.8, we're subtracting off the 87.8 here. That's negative 7.8 points. The fact that this is negative indicates the fact that the 80 points was below the mean. It was 7.8 points below the mean. And so forth. We subtract off the mean. This was way below the mean. This was above the mean. That's a positive deviation. Below the mean, above the mean. All right. So these are the deviations from the mean in this column. Now a student might ask, so as a measure of spread, why don't I just take the sum or the difference of these deviations? Well, try this out on your calculator. What is the sum of these deviations? And for that matter, what's the average of these deviations? It turns out that the sum and the average of these will be a big ol' 0. How's that for a measure of spread? I don't think so. We have some different scores here. We'd only get 0 variance, variation, or standard deviation if these are all the same score. So it would be inappropriate to take the sum or the average. It would just be 0. The sum would be 0, the average would be 0. That doesn't tell me anything about spread. So what can we do to these deviations to make sure that the results here will be non-negative? Now, one response might be absolute value, and that is a possibility. That would lead to what we call the mean absolute deviation, or the MAD, the MAD. But it turns out that statistical theory doesn't like that as much. So what else can we do to these values to make sure that these results are non-negative? Well, we can square these values. And the square of positive and negative values will all be positive. So the square of negative 7.8 is positive 60.84, and so forth. We square these deviations. Now in practice, we would normally fill out the table row by row. So once we calculate the mean, take the 80 points, subtract off the mean, we get the deviation, negative 7.8 points. And while that's still in your calculator, you would square that, and the result will be 60.84. You know that these square deviations cannot be negative. Likewise, you take the 76, find the deviation from the mean, square that result while it's in your calculator, and you get this big number, and so forth. So as you fill out these tables, you should fill them out row by row to save time. You don't have to keep re-entering these numbers. All right, so now we have these squared deviations. And by the way, statistical theory likes what we're doing. It likes variance and standard deviation. Now, what do we do with these squared deviations? These are the things that we're going to average to get our population variance. How do we take the average? We take the sum and divide by 5, capital M, the number of values. All right, the sum is 520.8. We divide by 5, and we get the population variance. The variance, population variance, sigma squared, is the average of the squared deviations, the sum of column 3, the sum of these values, divided by 5. We get 104.16, and it's a weird unit. It's in square points. What's a square point? Good question. That's one thing we don't like about variance, the fact that the unit often doesn't make sense. And by the way, we could round this off to 104.2 square points, but we're going to use this to find the standard deviation, the population standard deviation. So I'll keep this exact for now. This is exact. All right. So the population variation will in fact be exactly 104.16 square points. Now, one reason why we prefer the population standard deviation, the SD, over the population variance is that the units for standard deviation are natural. They're going to be in points, like for the original data values. So step 5, the standard deviation, sigma, is the square root of the variance. The square root of 104.16 is about 10.2 points. We round off to 1 decimal place because the original data values were in integers to 0 decimal places. The population standard deviation of the data is about 10.2 points. And it shares the same units as the original data values, good old points, which makes total sense. Now on your scientific calculators, you should have a sigma or sigma sub capital N button that will allow you to work out population standard deviation. If for some reason you need the variance, you could do what to these values? You could square them. Because remember, standard deviation is always the square root of the variance. I'll do this in blue. Standard deviation is always the square root of the variance. The variance is always the square of the standard deviation, whatever the context. All right. And how would you do this on Excel? All right, so let's say that we have 5 test scores for the 5 test students. For the population standard deviation, it's equals, you need that for commands, STDEV for standard deviation, dot P, that's for the population standard deviation. This is full census data. It's a population data set. Parenthesis, I can sweep over the entries. It's A2 to A6, and the parenthesis, and we get, lo and behold, it's about 10.2 points. It verifies what we got over here. For the population variance, you can just square that or directly equals, it's var.p for population variance. For these data points, 104.16 square points. Okay, next up, how do we work out sample variance and sample standard deviation? How's that a bit different? Next time.
Any questions? Any questions? Just a few more minutes. Sample data. All right. Whoops.
Hi, everyone. So for population data, how could we
Let
calculate
me,
a population variance?
let's go to the last one.
Hi, everyone. Let's say that instead of population data, we have to rely on sample data, such as the results from a survey. Well, if we have sample data of size little n, we can calculate a sample mean, x bar. And from that, we can calculate a sample standard deviation S and a sample variance S squared. In fact, we're going to calculate the sample variance first, just as we calculated the population variance first last time. Now, we want the sample variance to estimate the population variance of the population from which the sample was drawn. So ultimately, we might care about the population variance up here. But we can't get that exactly because we don't have the full census. We don't have the full population data set. So instead, we may have to draw a sample and rely on the sample variance. But again, the purpose of the sample variance is to estimate the population variance. We don't care about S squared in and of itself. We may only care about it in the sense that it helps us estimate sigma squared, the population variance. The same for S and sigma. So here's the formula for sample variance. And the standard deviation, again, is the square root of the variance. You'll notice that it's different. I'm going to go back to the formulas for population variance and standard deviation over here. So compare these two. Population variance over here, sample variance over here. Actually, I should reverse the colors. Oh no, this is fine. Blue here, red here. Okay. So many of the differences are in notation, right? Instead of sigma squared, the population variance, we're finding S squared, a sample variance. Instead of a population mean mu as our center, we're going to use the sample mean x bar as our center. Instead of population size capital N, we're dealing with sample size little n. So everything I've said so far has involved a difference in notation based on the fact that we're talking about sample data versus population data. But there is one computational difference. Here, for sigma squared, the population variance, we're dividing by capital N, the population size. Here, for sample variance, we're dividing by not the sample size, little n, but little n minus 1. There is a bit of a technicality here. So why is that? Why do we divide by n minus 1 here in the S squared formula? Well, here's the reason. Remember that we're supposed to plant our flag for the data set at the population mean. But here, when we're analyzing sample data, we don't have the population mean available to us. We just have a sample mean. The problem is that the sample mean is often an imperfect estimate for the population mean. There's some variability that's thrown in. The fact that we're using the sample mean, x bar, as opposed to the population mean, mu, that throws in a wrench, that throws in some more variability, which means that in order to better accomplish the goal of estimating sigma squared, and that is the goal of S squared, the goal of S squared is to estimate sigma squared, the population variance. Okay, but because of that whole x bar versus mu issue, we have to inflate the fraction a bit. Folks, let's say you have 1/3 of a pizza versus 1/4 of a pizza. Which is more pizza, which is less pizza? We have two fractions, the tops are the same. The 1/4, however, is less pizza because the denominator is bigger. The 1/3 is more pizza because the denominator is smaller. So when you go from 1/4 to 1/3, okay, then you're actually growing the pizza. So by dividing by n minus 1, we're actually inflating the estimate for sigma squared because of this wrench. All right, and again, S is the square root of S squared. We throw in the radical. All right. So I call this kind of a tilted average of the square deviations, the sample variance. It's inflated. All right. So let's say that this is sample data. There are 1,000 students in the class, a large lecture class. My TA, Igor, at the end of the exam, throws the 1,000 exams in the air and randomly grabs 5. By the way, what would be the problem with Igor just grabbing the first 5 exams off the top of the stack? Well, there could be some bias there, right? The last students who turn in the exam. Now, we don't know if they're the more conscientious students or the students who really needed the time, but there could be some biasing from doing that. So let's say that Igor randomly grabs the 5 tests from the air, right? This is our sample, our simple random sample. These are our 5 sample data points. Now, the calculations are very similar. We have these 5 x values. The sample mean is obtained by adding the 5 scores and dividing by 5, 87.8 points. Again, these are the same 5 numbers as before for population data. We subtract off the sample mean, but again, we're dealing with the same numbers here. We get the same deviations, and they still add up to 0. We square these deviations, and we get the same values over here. So everything in these 3 columns is exactly like what we saw for the population data set, except we're using different notations. We're using x bar instead of mu. Now, to get the sample variance, what do we do with these square deviations? We take a tilted or inflated average. We add these up and we divide by, not by 5. To get the sample variance, we don't divide by 5, we divide by 4, n minus 1. The sample size minus 1. And we get 130.2 square points. The square root of that is about 11.4 points, the regular unit. All right. On a calculator, you might see an S or this weird symbol, sigma sub n minus 1. I think S is a better symbol, but that calculates sample standard deviation if you input data. On Excel, right, to find the sample standard deviation of this data set equals stdev dot s, sample standard deviation for this column. We get about 11.4 points, okay, as we got over here, right? And then for the variance, we just square that or work out equals var dot s for this column, and we get 130.2 square points. Again, like what we saw over here. Well, now, so what? So what that the sample standard deviation is 11.4 points? What can that tell us about the class of 1,000 students overall? We'll talk about applications and interpretations of standard deviation next time.
All right. So you can basically do everything through lesson 9, except maybe some of the interpretation ones near the end. All right. Okay, any questions? We'll continue with lesson 9 next Monday. Any questions? Anything in public? I will now stop the recording.